What I'm going to tell you now is how you find the eigenvalues and also how you find the eigenvectors. And you have to do it from one equation. So let's see how that works. So we're looking at the matrix eigenvalue problem, where you have a matrix A, and it's n by n, and you multiply it by some vector v, and then it should be equal to lambda times v. So you have to find a solution to that problem. I start by moving this to the other side of the equality sign. So you have this equation, and now I'm doing a trick because I want to write it as a matrix vector product, all of this. And in order to do so, I introduce here the identity matrix. That is, I write this as A times V minus lambda, and then times E times V equal to 0. By doing this, I'm not changing anything, because the identity matrix, the one with ones in all of the diagonal and 0 elsewhere, doesn't change this. This is equal to V, so this is okay. But what I can do now is that I can put V outside a bracket. So now I have my equation. This is equivalent to this equation. Aha. Now you recognize something, because if this is the coefficient matrix, then this is a homogeneous system of linear equations. And you know a lot about that. What is the solution to this equation if this coefficient matrix is regular? Yep. The solution to this equation, if this coefficient matrix is regular, is only the 0 solution. You only have the 0 solution, because if this coefficient matrix is regular, then you know that the inverse exists, and you can multiply with the inverse from the left. And here you get the identity matrix then, and then you get just the v vector on the left-hand side. On the right-hand side, you get the inverse of this matrix times the 0 vector, and a matrix times the 0 vector is always 0. Is always the 0 vector. So if it is regular, then you only have the 0 vector solution. And this is not interesting. So you must demand, in order to find proper eigenvectors, you must demand that this coefficient matrix is singular. That is, it's not regular. This matrix here is also known as the characteristic matrix. Now, if I'm going to find the lambda values, you see the coefficient matrix here depends on lambda. And now I'm going to find the lambda values that makes this singular. How do I go about doing that? And you mentioned something about the determinant, and that is correct. For a singular matrix, you know that the determinant of the matrix is 0. So I simply look at this equation. A minus lambda E equal to 0. And I can say that this equation determines the eigenvalues. The eigenvalues for A, the matrix A. Now, how does it look, this equation? And now I'm going to do a simple 2x2 example. You have A is 5, 3, minus 6, and minus 4. I'll use this example throughout the lecture. And I'm going to compute the determinant of A minus lambda E. This will be the determinant. And remember how we write this? We just subtract lambda in the diagonal. So you get 5 minus lambda minus 6, 3, and then minus 4 minus lambda. And you have to then calculate the determinant here. So, and it's a 2x2 matrix, so the result is, if I multiply it out, 5 minus lambda times minus 4 minus lambda, and then plus or minus 3 times minus 6. And I get lambda squared, and then I get minus 5 lambda plus 4 lambda, that is minus lambda, and then I get minus 20 plus 18, that is minus 2, and I want to solve this equation. So a 2x2 matrix yields a second order polynomial. So if you have an n by n system, n by n matrix, you get an nth order polynomial. So let's try to find the eigenvalues here. I just put a name to this. This is the characteristic polynomial. And the way to solve it is just to calculate the discriminant. That is 1 minus 4 times minus 2 times 1, that is 8, 9. So the solution is lambda equal to 1 plus minus 3, the square root of this one, divided by 2. And then you have that lambda 1 is equal to 2, and lambda 2 is equal to minus 1. That is, you get 4 divided by 2, and you get minus 2 divided by 2, that is minus 1. So this is the solution to that problem. Let me take a little more evolved example. I take now a 3 by 3 matrix. 0, -2, 0, 1, 3, 0, and then 0, 0, 1. And I can immediately write down the polynomial that I'm gonna solve, because I want to find the determinant of this matrix minus lambda. I subtract lambda from the diagonal. 1, 0, -2, 3 minus lambda, 0, and then 0, 0, 1 minus lambda. And this is fairly easy to solve, because you see you have a column here, for instance, with 2 zeros. So you can make an expansion along this column here, and you get plus, minus, plus, minus, plus. So it will be 1 minus lambda, and then the determinant of this submatrix here, minus lambda, 1, -2, and then 3 minus lambda. And I have this minus lambda, and then I get minus lambda here times 3 minus lambda, and then -2 times 1. And if I multiply this out, I keep this first factor here, and then here I get lambda squared, and I get -3 lambda, and then +2. And you see here it's a 3 by 3 matrix. So if I multiplied this into this bracket here, I would get a third order polynomial, a cubic polynomial. So that matches. Now, again, when I solve this, I could compute the discriminant. That will be 9, and then -4 times 2, that's -8. So the solution here is it's 3 plus minus 1 divided by 2, and this is 2 and 1. So now you can read the eigenvalues. That is, you have lambda equals lambda 1 equal to 1. This is a factor here, but it's also a factor in this one. So this is one of the roots. So what you say is that the algebraic multiplicity of lambda 1 is equal to 2. Then you have lambda 2 is equal to 2, and here you have the algebraic multiplicity is equal to 1. And here, if you add them up, they add up to 3, which is also the dimension of your system. Now, what I'm going to talk about today and what you are going to see in the exercises is that the situation, or in other words, if you count with multiplicity, as we do here, then you can say that the characteristic polynomial always have n solutions. Well, it could be real or it could be complex, but it always have n solutions because it's an n order polynomial, and if you count multiplicities, then it has. So I can write here A is an n by n matrix. And it has exactly n eigenvalues when we count with multiplicity. Okay. Now, the question is there also n, say, linear independent eigenvectors? And this is what we're going to discuss now. So I just go over here. So now we're going to find the eigenvectors. So I'll just how to find eigenvectors. And this is, we're going to find the eigenvectors when we have found the eigenvalues. So let me take the example up here. So I write it again. 5 minus 6, 3 minus 4. And it has the eigenvalues lambda 1 equal to 2 and lambda 2 equal to 1. So, and you do it eigenvalue by eigenvalue. So let me put in the eigenvalue 2 into my equation. Remember, A, this is a characteristic matrix. Yeah? Yeah, you're right. Thank you. Minus 1. So you put it into your characteristic matrix, this lambda value, and then you have to solve this equation. Again, this is a homogeneous equation with a known coefficient matrix. So I could immediately write down the augmented matrix for this. Let me do this. So the augmented matrix reads, I have to subtract 2 from the diagonal. So I get 3 here, I have minus 6 here, and then I have 3 here, and then I have to subtract yeah, I have to subtract minus 4 or 2 from this one. so I get minus 6. And then the right-hand side is 0. So I have this augmented matrix. And here it's easy to, I take R2 minus R1, then I get zeros down here, and then I take 1/3 of R1, and I get trap of the augmented matrix. It's equal to 1 minus 2, 0, and then 0. And remember, when you have the augmented matrix, then you should write down the equations that corresponds to this augmented matrix. If I call my v vector for v1, v2, then the first equation gives me is equal to 0, and the second equation gives me nothing. So I can solve this as, and that is if I put v2 equal to a parameter t, then v1 is 2 times t, and I can write down the solution as t times v2 is t, so I have a 1 here and I have 2 here. So the eigenspace corresponding to the eigenvalue 2 is equal to the span of this vector 2, 1. Or I could write it in usual vector form like this, 2, 1. Let me just compute the other eigenvector space. I have A plus 1 times E, or it should be multiplied by V, and it's equal to 0. Again, I can immediately write down the augmented matrix. I get, so I have 5 minus 1, that is 6, and then I get minus 6, and then I have 3, and then I have minus 4 minus 1, that is minus 3. I want the right-hand side as well in the augmented matrix. You see the two rows here are proportional, so I can remove one of them and put zeros, and then I can divide, say, this by 6, so I get 1 minus 1. So I immediately get the totally reduced matrix as 1 minus 1, 0, and then 0, 0. And using this notation here, I get that v1 is equal to v2. This is simply the first equation that is solved in this way. And if I put this equal to a parameter t, then I can write down the solution as t times 1, 1. And then I get that e minus 1, that is the eigenspace corresponding to the eigenvalue -1, is the span of this vector. 1, 1. Okay. I take the other example here, and I want to find the eigenvectors corresponding to the eigenvalues down here. And remember, over here, I only, even though it is a 3x3 system, I only have 2 eigenvalues. Let's -2, 3, 0, 0, 1. And it has lambda 1 equal to 1, and the other eigenvalue is 2. So let me try to find the solution when lambda 1 is equal to 1. Then I get 1 times and again, I can immediately write down the augmented matrix. And this, I get a -1 here, 1, 0. Here I get -2, and I subtract 1 from here, I get 2. And here I subtract 1, I get 0. You see, these two are proportional, so I can replace this by only zeros. And this gives me, I can write down, so if I replace this by zeros and then I multiply the first line by -1, I get my trap T as this matrix 1, 1, 0, 0, 0, 0, 0, 0, 0. Let me see if I can do this here. Now, if you look at this, sorry. Thank you. Yeah.
Are you using the right-hand side from the augmented matrix?
Yeah. Yes, I am. I am so happy that you are awake, so that's good. But you see here, the rank, there's only one leading, 1. And so the rank of this matrix is 1. So how many free parameters do you have in your solution to that problem? Yeah, you have 2. Because the order of the system is 3, you have 3 equations, you have 3 unknowns, and the rank is 1, so you have 2 free parameters. So let us solve this. I can say that the only equation that comes out of this, if I write the solution as V1 or V2, V3, this is the three coordinates, and is that from the first equation I get that V1 is equal to V2, and I can put this equal to a free parameter. But also I can put V3 equal to a free parameter, because V3 doesn't enter into this equation that is left. So that's possible. And in this way I can write the solution let's say I can immediately write down V1, V2, V3, and this is S, and here you have, no, it's T, and we put V2 equal to T, so you have a 1 here and a 0 for the S. And if you look at the equation, here you get also a 1 here, a 0 here. And then S, you put V3 equal to S, and then a 0 here. So I get that E1 is equal to the span of these two vectors. What you then say, we're going to discuss this on Friday at more length, but you then say that the geometric multiplicity of lambda 1 is equal to 2, because you have two independent eigenvectors. So I should state this. This is the geometric multiplicity. Let me try to illustrate this. You have, say, x, y, z here. And let's draw these two vectors here. You have 1, 1. So this is the one eigenvector. 0, 0, comma 1. This is another. So this eigenspace E1 is simply spanned by these two vectors. So if I can draw this, you should imagine that this is simply the eigenspace corresponding to lambda equal to 1. And let me just find if the eigenvalue is 2, then you should solve this equation, a minus 2e equal to 0. Now I have put in the other eigenvalue, and I write down the augmented matrix. I get minus 2, 1, 0, 0. That is minus 2 at that place, and then the others are unchanged. And I get minus 2. And then if I subtract 2, I get 1, 0, 0. And for the last equation, I get 0, 0, minus 1, 0. I can subtract this from this to get all zeros here. I can multiply this by minus 1 to get a 1 here, and then I can interchange the two rows here, and then I can divide the upper row here by minus 2 in order to get my totally reduced augmented matrix. And this is 1 and then minus 1/2, 0, 0, and then I get 0, 0, 1, 0. I interchange these two rows, and then 0 all over. Now you have two leading ones, so the rank of this matrix, this augmented matrix, is 2. The number of unknowns is still 3, so you have one free parameter. If you interpret this as equations, you have 1, v1 is equal to minus, or plus 1/2. I moved it onto the other side, v2. And then I have v3 is equal to 0. These are my equations. Now, let me see if I can manage to get it here, down here. Because then the solution is, I put this as a free parameter. I put v2 equal to t. Then the solution is 1, 0, and then 1/2 and times t, where t belongs to. Now, when I write down the eigenspace here, I can in fact choose any vector parallel to this one. And often you would like to have integer numbers in your eigenvector. So if I put t equal to 2, I get 1, 2. So I get this vector here, 1, 2, 0, as the eigenvector. So I'll take a break for 10 minutes now.